Welcome to another module in this massive open online course. So, we are looking at the DTFT, the discrete time Fourier transform for the analysis of discrete time signals in systems, and in this module we will look at the DTFT for the analysis of discrete time LTI systems. Okay. So, we intend to discuss the DTFT, application of the DTFT for discrete time in particular. We would like to look at it in terms of the frequency response of these discrete time LTI systems. Okay, what is the frequency response? Okay. So, consider a discrete time LTI system with impulse response given by Hn. Okay. So, the input to this LTI system is Xn, output is Yn, okay, and Hn denotes the impulse response of this system. Denotes the impulse response of this system, and the input output relationship therefore. So, this is your LTI system. Okay. The discrete time LTI system with input given by Xn, output given by Yn. Okay. Hn denotes the discrete time impulse response of this LTI system. Okay. And now naturally we know that the output Yn is given as the convolution of Xn times Hn, or Xn is the input, Hn is the impulse response. Now taking the DTFT, discrete time Fourier transform, we have y omega equals x omega times h omega, which implies as usual the transfer function h omega equals y omega divided by x omega. This is the transfer function. Okay, is the frequency response of the LTI system or the transfer function. Frequency response of the transfer function. And now what happens if Xn is periodic? Now let us say Xn, the input signal is periodic. In that case, how do you obtain Yn given the impulse response, that is given h of omega? Now first observe that if Xn is a complex exponential, if Xn equals e raised to j omega naught n, okay, now the output Yn equals Hn convolved with Xn, okay, which is basically equal to, or which equals the summation of k equals minus infinity to infinity h k e raised to j omega naught n minus k, which is summation k equals minus infinity to infinity hk e raised to j omega naught n e raised to j omega naught k. Now, this e raised to j omega naught n, which is common, I take that outside. So, that becomes e raised to j omega naught n summation k equals minus infinity to infinity h k e raised to minus j omega naught k, which is simply h of omega naught, that is the dt of t at omega naught, that is summation h k e raised to minus j omega naught k. So, the output is simply given as h of, for the complex exponential at frequency omega naught, okay, the output is simply h of omega naught times e raised to j omega naught n. So, y n, so we have, and this is interesting, and we have already seen this. So, if x n is e raised to j omega naught n, then the output signal y n is simply a multiple scaled version of the input signal h omega naught times e raised to j omega naught n, and therefore, this is also known as the eigen function, okay, or the eigen signal. This is the eigen function of this LTI system, because the output is simply a scaled version of scalar multiple times the input. Okay. Now, if x n is periodic, then we realize that x n can be expressed as a discrete Fourier series. Then we have x n equal to summation k equal to 0 to n naught minus 1 c k e raised to j k omega naught n, where omega naught equals 2 pi over n naught. Okay, this is c k e raised to j. So, what is this? This is basically your discrete Fourier series. And this omega naught is basically the fundamental frequency. Okay. So, it is expressed as a multiple, is expressed as a sum of the complex exponential at the fundamental frequency and its harmonics, okay, k equal to 0 to n naught minus 1. This is the discrete Fourier series. Okay. Now, from linearity, now we know that corresponding to each e raised to j k omega naught n, the output of the LTI system is simply h of k omega naught times e raised to j k omega naught n. Okay. So, for each e raised to input, k omega naught n. Okay. Now, the corresponding output we have seen equals h of k omega naught times e raised to j k omega naught n, which implies for input of c k times e raised to j omega naught n gives the corresponding output c k. So, the input is scaled by linearity, output is also scaled. I am sorry, this has to be k omega naught n, and therefore, if input is x n equals summation k equal to 0 to n naught n minus k equal to 0 to n naught minus 1 c k e raised to j k omega naught n, the output by linearity, from linearity output is simply k equal to 0 to n naught minus 1 Ck h of k omega naught e raised to j k omega naught n. Okay. So, this is the corresponding output. Okay. So, this is your output to the periodic signal x n. Okay. This is output for periodic signal x n with period n naught. Equals 2 pi by omega naught. All right. You can see if the input is periodic, the output is also basically periodic. Okay. All right. And finally, for LTI systems characterized by difference equations, let us now look at similar to what we have seen before. Discrete time LTI systems characterized by difference equations. Okay. We have summation k equal to 0 to n minus 1. Let us say the difference equation is summation k equal to 0 to n minus 1 y of n minus k equals summation k equal to 0 k equal to 0 to n equals summation k equal to 0 to m b k x n minus k. This is the difference equation. Okay. This is the difference equation. Now, taking the dt of t, what we have is summation k equal to 0 to n minus 1 a k y omega. The dt of t of y n minus k is y omega e raised to minus j k omega, that must be equal to summation k equal to 0 to m b k x of omega e raised to minus j k omega, which means now taking the y of omega common on the left, I have y of omega summation k equal to 0 to n a k e raised to minus j k omega equals, taking x of omega common on the right, x omega k equal to 0 to m b k e raised to minus k omega, which means h of omega equals y omega by x omega equals summation k equal to 0 to m b k e raised to minus j omega divided by summation k equal to 0 to n a k e raised to minus j k omega. Okay. So, that is the transfer function. And taking the inverse dt of t of this gives the impulse response. Okay. taking the inverse dt of t of this gives the impulse response. Alright. So, basically that completes the analysis of the application on the properties of the dt of t, that is the discrete time Fourier transform for LTI systems with respect to the transfer function, the output for a periodic signal, output for an aperiodic signal, and also how to derive the impulse response and the transfer function of a dt of an LTI system described by a constant coefficient difference equation. Alright, so we will stop here and continue in the subsequent module. Thank you very much.